On October 9, 2022, the most powerful gamma-ray burst ever was detected by several space telescopes. The burst, officially called GRB 221009A, likely heralded the birth of a new black hole. And gamma-ray bursts are the most energetic phenomena in the universe since the Big Bang itself. They emit enough energy to sterilize entire regions of their home galaxies. Such events might occur in a galaxy once every few million years or so, but there are a lot of galaxies out there, so we detect gamma-ray bursts nearly every day. But GRB 221009A was so powerful it temporarily blinded the Fermi Gamma Ray Telescope. When the Gerald-Swift Observatory and xmm-newton telescopes imaged the bright X-ray afterglow, they found more than 20 rings of X-ray light scattering off dust clouds in our galaxy. It's estimated that a burst this powerful might occur only once every 10,000 years. And that means this was probably the most energetic gamma-ray burst to reach Earth since the dawn of human civilization. And that's why astronomers dubbed GRB 221009A the brightest of all time, or the boat. Since the initial outburst, a number of follow-up observations have been made at all wavelengths to figure out just what the hell caused it. And those findings have turned up a number of surprising results that call into question our understanding of gamma-ray bursts. For example, GRBs are thought to mark the beginning of a supernova, but neither Hubble nor the James Webb Space Telescopes found any evidence of one. And not only that, but it was surprisingly faint in the radio spectrum, despite the fact that GRBs should emit very strongly at all wavelengths. It was so weird and amazing that a series of papers about the boat were published in a special issue of the Astrophysical Journal Letters. So there's a lot going on here we want to talk about today, so let's get to it. Gamma-ray bursts are generally classified by their duration. Short GRBs last under 2 seconds and are thought to be caused when a pair of neutron stars collide. The collision sets off what's called a kilonova. By contrast, long GRBs can last anywhere from 2 seconds to several hours. It's thought that these longer bursts occur when the core of a very massive star collapses to form a black hole. Both scenarios produce an initial burst of gamma-ray emission followed by a longer-lasting afterglow. Now, the afterglow is created when the leading edge of the jet collides with the surrounding interstellar medium. The shock front produces emission at longer wavelengths, starting from X-rays but going all the way to radio. It's by studying the afterglow that we can learn about the properties of the surrounding medium, the physics of the GRB itself, and piece together the puzzle of what caused the burst in the first place. Now, if the GRB came from a black hole inside of a collapsing star, there's a third act to follow. The black hole's jet ignites runaway fusion inside the star's interior that explodes the star from the inside out. The result is an extremely energetic supernova, sometimes called a hypernova. These long-duration bursts are so energetic they can easily outshine their host galaxies. And we've detected some extremely bright bursts so far. But when GRB 221009A was first detected, it was without question the new record holder. However, the boat was so bright it actually blinded the instruments on the Fermi Gamma Ray Telescope. When its actual brightness was later reconstructed, the boat blew all of the other bursts out of the water. As a matter of fact, it was so bright it was detected by instruments that weren't even designed for this purpose. The very first detection was picked up a day earlier by Voyager 1, which is now in interstellar space. A day later, the burst reached the inner solar system and was detected by ESA's Gaia satellite at L2, and then the Integral satellite in cislunar space. About 1 second later, it was detected by Fermi and GRB Alpha in low Earth orbit. The burst even irradiated Earth's ionosphere. The burst continued to L1, where it was detected by the ACE and WIND spacecraft studying the Sun. And then a few minutes later, it was detected at Mars by MAVEN and Mars Odyssey. Something this bright doesn't happen very often. In fact, the boat was calculated as being a nearly once in 10,000 year event. Human civilization is only about 6,000 years old, so it's quite possible the boat is literally the brightest gamma-ray burst in human history. Lucky for us, we just happen to have telescopes in space that could study it. However, the boat is behaving in ways that really don't make sense. Bursts like these are understood to be associated with dying massive stars. But so far, the boat hasn't shown any evidence of a supernova. Not only that, but even though its afterglow was the brightest ever seen at X-ray wavelengths, it was surprisingly quiet in radio. So why wasn't it brighter at radio wavelengths, and why was it so extraordinarily bright to begin with? So we're going to investigate all this in a moment, but first, let's talk about keeping your personal identity safe with Incogni, the sponsors of today's video. I don't know about you, but I've been notified on more than one occasion that my personal information was stolen in a data breach. And that's because those companies are data brokers, and they're allowed to buy and sell your personal information without you even knowing it. The good news is that data brokers are required to delete your information upon request, but the bad news is the brokers are allowed to reacquire your information, so you have to follow up with them to keep getting them to take it down. Incogni solves this problem by contacting the data brokers on your behalf and requesting that your personal data be removed. But Incogni doesn't stop there, because they will continue to follow up with data brokers to make sure that your data hasn't reappeared and request that it be taken down once it does. Incogni is available risk-free for 30 days, so you can try it out for yourself and get a full refund if you aren't happy with the service. And Incogni has a special deal just for my viewers. Use the special code at the link below to get 60% off Incogni. Thanks to Incogni for supporting today's video. The boat was the brightest gamma ray burst ever detected, but weirdly, the boat's radio afterglow wasn't unusually bright at all. It gets even more interesting when you look at how the radio, visible, and X-ray emission faded out over time. And that's what we're seeing here in these data points. Each color corresponds to some time after the burst. Over the last 50 years of studying GRBs, a number of standard models have been developed that describe how the afterglow fades across different wavelengths. But when the models were run against the boat, they matched up with the visible and X-ray emission quite well, but largely came up short on the radio. The modeling also indicated that although the boat was the brightest ever seen, it may not have actually been all that powerful in terms of the total energy released. Rather, it may have appeared so bright because all of its energy was concentrated into a very tight beam, and that beam happened to be aimed directly at Earth. It's kind of like how a pocket laser is far more intense than a searchlight, even though it uses far less energy. Now, before you get any ideas, no, you should never, ever look directly into a gamma ray burst or a laser. It also turns out that the boat originated at a redshift of 0.15. And that works out to about 1.9 billion light years away. Believe it or not, that's actually not particularly far for a gamma ray burst. Something else that's really strange about the boat is that there was no supernova detected, even though long bursts are thought to come from dying massive stars. And the reason we believe that is because as the afterglow of the burst fades out, the underlying light from the supernova starts to become visible. So the light curve of the burst tends to stabilize and stay bright as the supernova takes over. But this time, there wasn't any evidence of a supernova as the afterglow faded. So what was going on? Well, for one thing, the boat came from a direction that was almost directly in line with the plane of the Milky Way galaxy. And that means its light had to pass through some 60,000 light years of our galaxy, which is laden with dust. If a supernova really happened, then dust in our galaxy could have blocked up to 99% of its visible light. Fortunately, longer wavelengths like near-infrared can sidestep much of this dust. To that end, the James Webb Space Telescope captured spectra of the boat at both near and mid-infrared wavelengths. In fact, this was the first time the mid-infrared spectrum of a GRB had ever been obtained. But if a supernova were taking place, there should have been some excess emission or changes in Webb's spectrum over time, but neither of those effects were detected. And that might be because there was more dust at work here than just that from our galaxy alone. Take a look at this near-infrared image made with the Hubble Space Telescope. The extended feature emerging from the burst is actually the burst's home galaxy. And that galaxy appears to be a spiral seen edge-on. And that means the supernova would have first had to have penetrated through its home galaxy's disk and then through the disk of the Milky Way before arriving at Earth. So maybe the supernova's infrared signature was weakened by 2 galaxies worth of dust. Or what if there was no supernova at all because the black hole that formed inside the collapsing star managed to kick off the gamma-ray burst, but then swallow its own supernova? It seems kind of weird, but in 2015, the massive star N6946BH1 disappeared without a trace. No supernova, no gamma-ray burst, nothing. It's possible that this particular star was a direct collapse black hole. The boat might present us with some new kind of intermediate case where a massive star's core collapses to create a black hole, which in turn kicks off a gamma-ray burst, but then the black hole gets so massive so quick it reverses and consumes the subsequent supernova. Or maybe there wasn't a supernova because the burst wasn't triggered from a collapsing massive star at all, but rather by a pair of colliding neutron stars. Such events trigger a shorter and less energetic gamma-ray burst. But if the burst was confined to an extremely narrow jet and aimed directly toward Earth, it would then make the burst appear bright enough to become the boat. But colliding neutron stars are thought to produce GRBs that are only between a few milliseconds to no more than a couple of seconds long. The boat's outburst lasted 600 seconds, and that's why it was assumed to be a collapsing massive star in the first place. However, in 2022, Rastinajad and collaborators reported the discovery of a kilonova associated with a GRB that lasted nearly a minute. So the boat would need to be a pair of colliding neutron stars that managed to create a GRB that lasted up to 10 minutes longer with an ultra-collimated jet aimed directly at Earth. That does seem unlikely. But then again, if nature does allow for these highly collimated, supernova-free, long-duration bursts to happen all the time, we still wouldn't be able to have seen one unless it were aimed directly at us. Maybe that's why we never saw one until now. Such jets would require extremely strong magnetic fields in order to collimate them so tightly. And such fields would polarize the emission of the initial burst. The stronger the magnetic fields, the more polarized the light. To that end, the Imaging X-ray Polarimetry Explorer, or IXP, measured the polarization of the afterglow. It found that while the polarization was high, it wasn't really the highest recorded for a burst. However, the boat was glimpsed through the plane of the galaxy. Light passing through galactic clouds scatter, forming the rings surrounding the burst. It's possible these dust clouds might have reduced the polarization of the light in some way, but they need more observations as the afterglow fades to know what effect the dust is really having on the polarization. The more layers of dust the light passed through, the more rings are produced. In total, 21 rings were counted, and that means the burst had to pass through no fewer than 21 clouds, ranging from as close as 700 light-years from Earth to as many as 61,000 light-years on the other side of the galaxy. However, not all of the light from the burst is passing directly through the geometric plane of the galaxy. The angle of incidence is about 4 degrees, so the most distant rings were formed above the plane of our galaxy. So why is there dust above the galactic plane? Well, it turns out our galaxy isn't perfectly flat, but rather has a warp on either end. On the far side, the warp is lifted upward, and that allowed just enough dust present for the boat GRB to pass through. So in a real sense, the boat allowed astronomers to probe at least a portion of the structure of our galaxy. We now know where the dust clouds lie along the line of sight to the boat, and that'll in turn tell us more about the history of our galaxy's formation, which includes mergers and collisions with smaller galaxies. This past winter, the boat disappeared behind the sun for a couple of months, but it has since reappeared and more observations are being conducted now. And that's good because there are so many questions left to be addressed and so much more to be learned. A huge thanks as always to my Patreon supporters who are helping to keep Launchpad Astronomy going, and I'd like to welcome Laura Sanborn as my newest supporter. And if you'd like to join me on this journey through this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, stay curious, my friend.